Okay. So, there are 3 ways of coming up with the reaction orders. So just to kind of review where we're at, reaction orders are this. So we have 2 reactants to form, well, I mean, you can have more than or less than, you can have only 1 reactant or 2 or 3. But anyway, the rate law expression is like this, where you take the molar concentration raised to the reaction orders. And and then sometimes it's on a test, and it's like, how do you find M and N? And your answer is always going to be reaction orders can only be found through experimentation. That's it, that's it, that's it. End story. So we said that we did by inspection, and then algebraically, and then the last one is graphically. But what they have in common is you have data to work with. So how can we go ahead and come up with those reaction orders graphically? Well, here's how this would work. I'm kind of building up to how we're going to do that. So the rate law expression is this, and of course the object is to find M and N graphically. So here's another thing, and I actually have my law of logs handy. We can go ahead and take the log of both sides of the rate law expression, and it looks like this. Now the thing at the bottom says we can either go log or ln, and as you know, log is base 10, and ln is log with a natural base, t. So anyway, we take it both sides. Now, according to the law of logs, if you have the log of a quantity, you can break it out into pieces, added together, so it looks like this. So all I did between the previous one and this one was to break out the natural log of the product of a raised to the m and k and b raised to the n. So here's the deal. Here's why I'm putting the molar quantity of b with k, because in this series of reactions, I'm going to hold b constant. Guess what else is constant? K. That's why I grouped it that way. Now, if we're trying to find something we can plot, okay. Let's see, what's the difference between now? Oh yeah, I see. What's the difference between this line and the first line and the second line? Well, I've applied the law of logs, which is awesome. The natural log of quantity a raised to the m is equal to m times the natural log of that quantity. So it's exciting. So finally, I get something I can plot. So if I go ahead, y is equal to mx plus b. So here along the y-axis, I know it seems weird, but I'm going to actually go with the natural log of rate. And here along the x-axis, I'm going to go with natural log of the molar concentration of A. It will actually have a positive slope, and the slope of the line will be equal to, I know it's weird, slope of line, the variable for slope is m, and actually this is the reaction order. 2 m's, go figure. M is equal to m. Okay, that's it. And this is actually, the sheet I gave you has this law on there. If we have the log, whether it's a natural log like this or the log base 10 of a product, we can break it out as the sum of the individual logs. And then also on the sheet, if you take the natural log or the log base 10 of anything raised to a power, you can bring that power up front. So like I said, the reason I kind of bunched molar concentration B with K was K is constant, B is constant, molar concentration B, just how I set up the experiment. All right, so like I said, I kind of built to this. If on the y-axis we put the natural log of the rate, and along the x-axis we put the natural log of the molar concentration. Voila! Okay. Part 2. So, and actually I'm going to take it a bit further. So if I run a set of reactions where B is held constant, I can find the reaction order of A. Well, if I run a second set where A is constant, I can find the reaction order of B. It follows a similar pattern where now if I plot again the natural log of rate along the y-axis, but now the natural log of the molar concentration of B along the x-axis. Then I can get the reaction order of B, which is N, be the slope. So again, this is, you guys are going to collect data tomorrow, and you're going to do this. And Benny's going to be out of town, headed to Boston. All right. So it gets even better. Wait, there's more. So you're going to have 2 plots for tomorrow. You're going to actually have 1 more plot for tomorrow. And this is to come up with the rate law constant K. So here's how this works. By this time in kind of the scenario, we know M, we know N, okay, and we're trying to find K. So simply, if we go ahead and plot along the y-axis rate and along the x-axis the molar concentration of A raised to its reaction order, which we know now, molar concentration of B raised to its reaction order, which we know now. Again, you'll get a straight line, and the slope of that straight line will be equal to the rate law constant K. Okay? That's it, man. So three ones. Okay? The one I didn't show you was very similar to this one. So that would be ln of rate, ln of the molar concentration of B, where you hold A constant, positive slope. That will give you the reaction order of B. Cool. Well, let's see what that looks like. So you're going to see some data for this reaction run. You're going to see it was run 8 times, 4 times holding 1 variable constant, 4 more times holding another variable constant. We come up with reaction orders, we do 1 more plot, and we come up with rate law constant K. So, okay. So here's the first 4 experiments, and you can see that the initial concentration of the O2 is held constant, so I can get the reaction order of NO. And in this last set, I hold the initial concentration of NO constant to get the reaction order of O2. Notice I have rates over here are in moles per liter per second. That works. And it should follow a trend that we've been talking about. As we increase the initial concentration of any reactant, as long as it's a positive reaction order, which these will be, notice that the rate increases. Increase the molar concentration of the O2, the rate increases. It's always nice to say, yeah, that makes sense. These were all run at 25 degrees Celsius. So, here we go. This is the first 4 runs where the O2 is held constant. This is the varying constant. You might recognize this. This looks like graphical analysis, or logger pro, excuse me, logger pro. This is your raw data. We know that we can create calculated columns, so we need to create a calculated column for this, for this one, natural log of rate. We need to come up with a calculated column for this one, natural log of the molar concentration of NO. And then we're going to plot these. This first blue one will be on the y-axis. The second blue one will be on the x-axis. And it will look like this. And again, your slope is what we're looking for. And I said we're going to focus on 0, 1, and 2. And to me, I'm kind of liking 2 for that. Slope is approximately equal to 2. So the reaction order of NO is 2. Score 1 for the team. Okay, the other set of the other 4 runs, we're changing the O2, holding the NO constant. And then, so we need to take the natural log of the O2, the natural log of the rate. Okay, put the natural log of the rate along the y-axis, natural log of the O2 along the x-axis. And again, a nice straight line, positive slope. In this case, the slope is equal to 1.02, like in reaction order of 1. Perfect. Combination coefficient looks like it was dry labbed. Okay. So now we know our reaction orders, and now we can actually do this one to come up with our K. So our rate law expression without solving for what the K is looks like this, where the rate is equal to the rate law constant K times the molar concentration of NO raised to its reaction order, which is 2, times the molar concentration of the O2 raised to its reaction order, which is 1. The overall reaction order is 3. And like we said before, whatever the overall reaction order is, that actually sets the units for what K will be. I have kind of a slide to kind of talk us through that. So to do this last little bit where we're coming up with the K, we need to have all, and again, this is what you guys will do with the data you'll collect tomorrow, which you'll need to write a semi-formal lab report for. Not getting off the hook for this one. So we need to have all 8 trials, the molar concentration of even the one that was held constant. Okay. Then we need to create one more column because we're going to plot rate along the y-axis, and along the x-axis is the molar concentration of the reactants times each other raised to the reaction orders, which is 2 and 1. So that's what's done in this last column. And let me know if you have any questions, but Logger Pro does a pretty good job of all that. So we're going to square this column because it's second order, and we're going to multiply it by the second column, raised to the first power. Okay. So then we will plot the last 2 columns. That looks like this, where now we have 8 data points. Not bad. And the slope then will actually give us the value of K. So our slope, you're looking at 7.1 times 10 to the third. And I'll kind of talk you through, this is, the units are actually, well, let's talk units here. The overall reaction order is third, so we're going to have to clean up what's introduced by your molar concentrations. Okay. But bottom line units are liters squared per mole squared, also in the denominator is time. And that will leave you with rate, units of moles per liter, that is what you need by introducing a Q. So this is to kind of talk you through how the units work out. So rates are always going to be moles per liter per time. And you figure this is one way to think of it, by introducing something raised to the second power, which is your NO, something raised to the first power, which is your O2, you introduce moles cubed per liters cubed. So in order to get it down to moles per liter, you need to introduce a liter squared per mole squared. Okay? I know. All right, on to part 3. Parts is parts. Okay, so I'll try to kind of, bless you. Part 3 will have some equations. I'll put it this way. You will get an equation sheet for your Unit 2 exam also. So don't be freaking out with these equations we're going to see that are developed related to rate law or reaction kinetics. These equations will be on your next unit exam. You just need to know how to use them. Sounds like a threat. It's not. Okay. So compare and contrast. Up to this point, what we did, I'll write it this way. Up to this point, we ran specific trials. So trial 1, 2, 3, 4, 5, 6, and came up with rate. My point here is we ran multiple trials and came up with rates. I'm switching it up now. Now, I'm going to run one trial, and I'm going to have time, and I'm going to have molar concentration How many trials? One trial. It's called time concentration data for one trial. And I'll show you how we can actually now use that to our advantage. Just wanted to kind of point out, I feel like we're switching gears here. So time versus concentration. Reactant concentration is measured over time. Now sometimes you can get this kind of indirectly by measuring the molar concentration of something else and using stoichiometry. So this is called time concentration data, and we can use this to get to reaction orders too. I did lie when I said reaction orders. How do you get to them? You can either do a by inspection, a graphical, that's the third one, or algebraic. That's true, but here's another way. Okay, time concentration data. Okay. So I'm going to talk you through your only options. These are kind of limited, but they can be expanded to other reaction orders. I'm going to focus on, we're going to talk you through a proof. If it's reaction order 0, reaction order 1, reaction order 2. Again, this can be applied more generally, but we're going to just focus on those. Okay, so there'll be these tests, first order test, second order test, 0 order test. And it will either pass the test, your time concentration data will pass the test, or it will fail the test. It's like a pass-fail. Oh yeah, and the other thing is you can identify which reaction order is 0, 1, or 2, and you can knock out the rate law constant K. Each one of these tests required, I will warn you ahead of time, that the homework associated with this, you're going to have to plot, so you're going to have access either to graphical analysis, or if you're a good Excel spreadsheeter, you can actually, as far as I haven't thought through it much, but I think you can use Excel to use this too. So let's start with 0 order. Well, what do we know about 0 order? 0 order is kind of funny, I think, because that means that the superscript of the molar concentration, it's raised to the 0th power. We know that's equal to 1, right? So a 0 order means that actually the rate, the molar concentration has no effect on the rate, which is kind of interesting. But let's see what sort of test we can come up with. Okay, so if it's 0 order, that means rate is equal to K. Well, the rate then, we know that for tracking a reactant, the rate will be negative change in that molar concentration of the reactant over time, because the change will be negative and the rates have to be positive. Okay?
So is it possible that it was on the homework? Because I was doing the homework yesterday.
Okay.
And I couldn't, when they ask you to find the
change in concentration of the
rate of disappearance.
Right.
And I looked at the answer keys on the homework, and it was an equation like that, and I couldn't understand. I didn't understand.
You had the negative in front of it? Okay.
And sometimes it was negative, and sometimes it was just positive, and I couldn't understand why.
I think I know what you're describing. So the thing about if you were to do a delta A change in molar concentration A, it's always final minus initial,
Okay.
and your final is less than your initial. So the delta A is going to be negative if it's a reactant. And so if that's negative, you have to introduce a negative sign in front of you're going to get negative, and to make it positive, you introduce a negative.
Because the rate has to be positive.
Because the rate has to be positive.
Okay.
And I think sometimes in my answer keys, or I've seen it written with the absolute value signs, which works too. Okay, but if you're tracking the change like we are in the molar concentration of the reactant, it's going to be negative, so disappear.
Mm-hmm.
And so then that means if you want your rate to be positive, you're going to take it times -1.
That makes sense.
Yeah. Lost my pen. There it is. Okay. So we could actually do, we could integrate both sides. It's been so long since I've done this. But we come up with this integrated time concentration equation. And this actually, will this be on your unit exam? It might. So I'm going to divide this into 3 places. This is 0 order. This is first. This is second. Okay. So the integrated time concentration equation looks like this, that the molar concentration of A at any time t minus the molar concentration of your initial A is equal to negative KT. I'm not sure, like I said, if that will be on there. We're going to rearrange this. Okay. We rearrange this, and this might be another form. I don't know, maybe this is in even a better form. The molar concentration at any given time, this is if it's zero order, will be at any time, molar concentration at any given time will be equal to negative KT plus your initial molar concentration of A. Now, I told you, maybe I didn't tell you, but we're going to have plots for each one of these. So what can we plot? Well, if along the y-axis, we plot just the molar concentration of A, and along the x-axis, we plot time, you should get a negative slope and this a line, straight line, and the straight line will have a negative slope, and the slope will be equal to negative k. That's it, if it's zero order. It's a zero order test. So like I said, it's a pass-fail test. If you do this plot and it's not a straight line, it fails the test and it's not zero order. That's as simple. If the plot is a straight line, then you know k. Zero order, k is equal to the m, the slope. Sorry. I'll say m is equal to negative k. If you try this and it's not straight, it's not zero order. Okay? We'll do that for the two others. That's zero, first, second. Oh. So for instance, I've got two lines here, two curves here, and notice that this is a test for zero order. How do I know that? I'm plotting the molar concentration of a reactant versus time. Zero order test. Straight line, not a straight line. Okay? So we say the decomposition of SiO2 fails the zero order test. The decomposition, you know what I mean, of tungsten, it passes the zero order test.
Which test?
The decomposition of W, tungsten.
Straight.
Because it's straight. Yep, that's it. That's totally it. Okay, first order. What do we got there? Well, if it's first order, then our rate law expression looks like this. Rate is equal to K times the molar concentration of the reactant raised to the first power, because it's first order. We could go ahead and say this about it, that rate is equal to negative change in A or change in time. You could go ahead and integrate that, and this is what it looks like. So again, this is going to be, I'm going to give you an equation sheet, but you have to recognize this relationship, important relationship for with regard to first order reactants, that the natural log of the molar concentration at any time t, the ratio of the molar concentration of A to the initial molar concentration of A is equal to negative KT. That's pretty cool. I'll go ahead and jot that other one down here. And actually, we're building up to, that's a good one we can use for, go ahead and plot. So we can break this out, and if you have the natural log or the log base 10 of a ratio, you can break it out as, you can break this out as the natural log of the difference. So that's be the natural log of A minus the natural log of A0, and actually that's on the logs that I gave you. So you can get it into this form, and so we are ready to plot. You can see how much I memorize it, yeah? Since you don't have to memorize it, why should I? All right, so y is equal to mx plus b. So here we go. Here's our first order. The natural log of the molar concentration of A versus time. Again, it will be a negative slope, and the slope will be equal to negative K. That's it, man. First order test. Straight line passes, not straight line fails. Sometimes it's hard to be like, oh, it's kind of curvy. Well, go curvy. Okay. You can actually use, we've used a straight line test correlation coefficient. The closer it is to a -1 or a +1, it's got a positive slope, then the straighter the line.
So the zero order test was also straight though?
Yes, they're both, each one of these tests is straight line.
Oh.
Yeah, but we change up what's plotted. So far we've changed up, and we'll roll for the second order, what's plotted along the y-axis. Yep. Time concentration data. So we can draw these conclusions. If we plot this, and what this is natural log of A versus time. If you do one of these, and it is a straight line, it passes, and you know now, then the slope is equal to -k. If it's not straight, then it must not be the first order. So 0, first, second. Here we go. Second order. Oh, sorry. So here's an example, just like we talked about. When you look at the axes, look at the specifically, you know, we have time along here, but what's along the y-axis means what test we did. This is the natural log of A. That must be a first order test. And notice that, again, natural log of the molar concentrate, natural log of A, the reactant, trying to check for first order, but like the caption said, this fails first order. And you'd be like, can you kind of see the curve there? Okay. So 0, first, second. What does that look like? So we're going to kind of do a similar thing. Our rate law expression then must be equal to the rate law constant K times molar concentration of reactant raised to the second power. So we can say the rate is equal to negative change in A over change in time. Go ahead and integrate both sides, and you end up with this relationship. It's almost like magic. Okay, so we have this. It's weird. The inverse of the molar concentration of A at any time t minus the inverse of the initial molar concentration of A is equal to positive KT. Shoosh. If we rearrange this, then we get this. The inverse of the molar concentration of A is equal to KT plus the inverse of the molar concentration of the initial molar concentration of A. Inverse of yeah. And that one actually is getting, so we can go ahead and plot it. So what our plot would look like was, this is our Y is equal to mx plus b. So Y is equal to mx. And now we should have a positive slope. And now the slope is equal to K. Nice. So if you see somebody has time concentration data and they have done an inverse of the molar concentration of a reactant, plotting that along the y-axis, yeah, that means that they must be checking for second order. So we can make these kind of similar statements or conclusions about that we did the first and the zero order. You know, if you do this plot and straight, ding, 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 you have passed and you have found something, a reactant that's second order. If you do this and it fails to be straight, it's not second order. And if you go ahead and it is second order, from the slope, you can just pick off the K. Here you have to take it, you know, K is equal to negative slope, but that's okay. We can do that. So if we take that, the same data that we looked at before that failed the first order, passes the second order. So, notice along all of these, we have time is along the x-axis, but we change what's along the y-axis. Aren't you glad you don't have to commit that to memory? The hardest part, though, is you have to remember which is which. Okay? And actually, we will be doing, we don't have class on Friday, not class Friday. But next week, we will be doing more with these integrated time concentration equations. So they are more than just this. Okay, so let's look at an example. Say we have time concentration data for this decomposition. Okay, all right. So there's the time data, and here's the molar concentration of the reactant. As you might imagine, the molar concentration of the reactant is going down. Oh, it never hurts to see, does this data make sense? Yes. So actually what you're going to see, what we would do in Logger Pro, or try it in Excel. I know some of you guys are having maybe a hard time having access to Logger Pro. Try it in Excel if you want. You're an Excel guru. What we're going to do actually is we're going to take that molar concentration and we're going to plot it versus time. Do you have a straight line? We're going to take that molar concentration, we're going to take a natural log, plot it versus time, see if we have a straight line. We're going to take that molar concentration, take the inverse, and plot it versus time, see if we have a straight line. That's it. That is totally it. So if you kind of, again, you will have a data sheet or a calculation sheet on your next unit exam. You just have to recognize that the zero first and second. Okay, so prepare those plots, look for a straight line. Whichever one we successfully get a straight line for, then we can go ahead and nab the K, the rate law constant, from the slope. If it's zero or first, we're going to have to take it times -1. And if it's second order, it is. It just is. Okay, so yeah. So here we go. This is actually the raw data. This is the time concentration data. Of course, regular old concentration is what we're going to go with for zero order test. For the first order test, we're going to take the natural log, and for the second order test, we're going to have to take the inverse of the molar concentration. So this is actually just kind of setting it up, getting ready for our 3 plots. And yeah, the homework is and if you're a slide counter, I'm telling you that we actually, even though we're not going to get through this whole thing, we will get enough so you can do homework. So why would I be if you didn't have homework over a long weekend? Okay. So this is zero order test. How do I know that? Well, we have time, which we have in all 3 tests, but along the y-axis we have the molar concentration. This is plain old molar concentration, zero order. Now straight. Okay, and actually, if you're kind of playing around and again, if you're using Excel, or I know Logger Pro, well, you can do like a curve fit. So this is a curve fit, so definitely not straight. A little straighter, still a little curvy. This is our first order check. How do I know? Because it's the natural log of the molar concentration. I'm not liking it. Now there we might have something. So this is the inverse of the molar concentration of the reactant versus time. Straight line should be positive slope, which it is. So remember, this is the one where actually then the rate law constant K is equal to the slope. Okay. So we have the 2 questions. We've answered one of the 2 questions. Must be second order. And this one of 2 questions. The other question is, what's the rate law constant K? It's the slope. And since it's second order, we know that the units of K must be liters per mole time, in this case seconds. Feels kind of anticlimactic, but that's it. So this is information that OpenStax kind of puts in a table like this. For 0, first and second order, if that's your overall, then we know that it sets the units of K. Integrated time concentration expression is this, what I have on the board here. Okay, this is what we plotted. Kind of clever, actually. How do we get K? We talked about. Okay, Now this half-life, this actually is going to be one thing we're going to talk about on Monday. We've got time to knock out that last one. I didn't look at it before, but we're going to go ahead and knock this one out. I don't think that's taking us very long. But the hope, you will know enough now to be dangerous. You know enough now to do the homework. So let's see if we change it up. What if instead of one reactant, you have two reactants? Well, we just kind of, and I think this is the experiment you're going to be doing a week from tomorrow. If we have two reactants, it means we have to hold one constant and kind of tease out the reaction order separately. Okay, so let's just say that we're going to hold B constant, and so then our rate law expression becomes this. Remember, we're going to hold B constant. Well, if B is constant, then we can kind of make this, I don't know if you remember, this prime, that means a pseudo constant. So all this is saying is, goodness gracious. Since this is constant because of how we're going to run the experiment, I can combine these two constants into what's called a pseudo constant, or K prime. That's all it is. Okay, so K prime, pseudo constant. We'll worry about that later. So what we said before is we can go ahead and now do a plot, a time concentration plot of the molar concentration of A, the natural log of A, and the inverse of A to kind of see what we got going on. So how are we going to keep B constant? It's kind of weird. We can keep B constant if we basically douse your experiment with a bunch of B. So even though B is being consumed, it's still got a bunch left. It's true. So what if we go ahead and we're selective, and we have two reactants, A and B. Now as A reacts, it'll go down, and as B reacts, it'll go down. But notice that A is like the more limited reactants. We talked about limited reactants and reactants in excess. So at the end, when the dust finally settles, when all A is consumed, we're still going to have almost 0.1 molar B. So essentially then, B is held constant. It's a trick. B will go down just a smidge. Oh, was that all I said? Okay, there's no problem for it. So actually, I think that technique, hold that dot a week from tomorrow. Time concentration. Okay, so like I kind of warned, you're gonna have to find either Logger Pro and then or else Excel. Dang. Hooty hoo.